celebrated in many countries as the Pi Day, because that date is written as 314 in some countries, and the mathematical constant pi, as you all know, is approximately 3.14. So now celebrations have taken place across the world officially. Our partner, the International Union of Mathematics, has taken an active role in organizing and coordinating celebrations for the International Day of Mathematics around the world through its membership and partner institutions. The theme of the year's celebration is mathematics for everyone. Until today, people and organizations all over the world announced over 1,041 events in their cities. I hope you will find this webinar useful and invigorating, as we have a number of distinguished speakers gathered for you today to talk about industrial mathematics. This is an exciting multidisciplinary field that applies mathematical theories and techniques to solve real-world problems in industry and in technology. If you have any questions for the speakers, please add your question to the chat box with the name of the speaker to whom the question is directed. Without further ado, I declare this session open, and I am very pleased to start the session with a message from the UNESCO Deputy Director General, Mr. Jing Chu, who is not able to join us today, but he recorded a message for us. Thank you.
Ladies and gentlemen, it is my great pleasure to welcome scientists, entrepreneurs, and young mathematicians to this year's celebration of International Day of Mathematics. This year, UNESCO wanted to draw attention to one of the most exciting and innovative areas of research in applied mathematics, industrial mathematics. We hope that this webinar will provide valuable insights into the role that mathematics plays in solving complex problems that arise in a range of industries. Modern manufacturing and service industries have been radically transformed by the knowledge economy. As we go forward, we shall rely heavily on mathematics to build a sustainable industrial system. Industrial mathematics is already helping, for example, to develop predictive maintenance models for wind turbines, which are subject to wear and tear from constant use and exposure to harsh weather. By using mathematical models to predict when maintenance is needed, wind farm operators can schedule repairs before their equipment fails. This reduces the amount of time that turbines are down and extends their life. To take another example, the field of natural language processing relies heavily on mathematical models and algorithms to analyze and classify data, and for tasks such as answering questions, identifying the emotional tones of a text, or machine translation. In particular, fast and economical computing, office products, the development and use of large databases and methods for refining requirements to meet new needs all rely on industrial mathematics. The fourth industrial revolution will be fueled by the use of mathematics by industry. The creation of a mathematical and statistical models and the development of numerical methods and algorithms to allow computers to find solutions to real-world problems. Artificial intelligence and other digital technologies will play a prominent role in research and business in the coming years. As the latest UNESCO science report revealed, many countries with different levels of income are prioritizing their transition to a digital and green economy in parallel. Mathematics will be at the heart of this transition. According to a report by the African Mathematical Union, industrial mathematics is one of the fastest growing areas of applied mathematics in Africa, with rising demand for mathematical skills in sectors such as mining, agriculture, energy, and finance. According to the African Institute of Mathematical Sciences, African demand for jobs related to mathematics is expected to grow at an annual rate of 15% over the next decade. What a paradox that, despite this huge demand, there should be a critical shortage of young talent in mathematics. That is why one important objective of this webinar is to open the eyes of young scientists to the many applications of mathematics in industry. We want to encourage young scientists to realize that mathematics offers exciting opportunities for their career development. Ladies and gentlemen, mathematics has been used by humanity for thousands of years, as demonstrated by the discovery of the Ishango fossilized bones, which revealed the practice of mathematics in Paleolithic Africa more than 20,000 years ago. Today, we are developing the quantum computer. The history of mathematics is the history of our ambitions, the history of ingenuity born of the desire to solve a problem. Despite the growing role that mathematics is playing in our lives, the majority of people are not very aware of the enormous contribution that mathematics and other basic sciences can make to sustainable development. That is why we are currently celebrating the International Year of Basic Sciences for Sustainable Development. The aim of this International Year is to raise awareness of the enormous contribution that the basic sciences have already made to sustainable development and make the case for raising the current level of investment in basic sciences. Mathematics should not be a language understood only by experts. I am, therefore, pleased to see that scientists are working to give mathematics a voice. A year ago today, on International Mathematics Day, we and our partners launched the English version of Mathematics for Action, supporting science-based decision-making. Today, we are pleased to announce the launch of the French version. With this book, our aim is to make mathematics more accessible to a wider audience. But to effectively support the basic sciences, we must act at all levels of society. That means starting from the earliest stages of education. It means reducing inequalities in access to science. This is why UNESCO is developing mathematics education and research in developing countries, with a particular focus on women and young scientists. We are doing this through our own educational programs, but also through our regional centers in Hanoi, Vietnam, and Accra, Ghana. We are also doing this through our university chairs in Benin, Nigeria, and Palestine. We are doing this through the programs in Asia, Africa, and Latin America run by the International Center for Pure and Applied Mathematics in Nice, France. Ladies and gentlemen, mathematics has its origins in the abstraction of a large number of real, practical human experiences. This means that mathematics is not only a tool, but also a way of thinking. If tomorrow's world turns out to be more sustainable than the world of today, we shall owe it in large measure to the leveraging power of mathematics to make a meaningful impact on the world around us. I wish you all a productive and enjoyable discussion. Thank you.
Thank you very much to our Deputy Director General for this insightful remarks. Now I would like to introduce you to Professor Muhammad Mustafa Fall, the President of the African Institute of Mathematical Sciences in Senegal. Professor Fall is a member of the International Mathematics Union Executive Committee and a board member of the UNESCO International Basic Science Program. Professor Fall will launch the French version of the UNESCO toolkit, Mathematics for Action, that was actually launched last year in English, and now we are launching it in French. So this toolkit was named as Mathematics for Action, Supporting Science-Based Decision Making. Professor Fall, the floor is yours.
Thank you, Maeve. Thank you very much, Amal. So I just want to see how to share the screen, which I want to do. So quickly. Okay.
Sorry, Professor Fall. Jean-Charles, could you please give Professor Fall the permission to share his presentation? Thank you.
Yes, I will see if I can do that.
Okay, in 1 minute. Oh.
Okay, Professor Fall, you can share now.
Yes, so
Can you see a green share screen button on the bottom of the Zoom?
I do see it. So I clicked on it.
Mm-hmm.
Everything is fine, I think.
Then you have a window that pops up and you need to select the square when you want to share your support.
Right, I think everything is coming now.
Okay, perfect.
Yeah. So thank you very much. Thank you very much, Amal. And I also start by wishing everyone here present a happy International Day of Mathematics. Alors, ma présentation donc, sera faite en français.
So I will present in French, since the toolkit that I have to present to you has now been translated into French. As you can see, we prepared a toolbox, which is a pocket book. And you can see from the cover that there are mathematical symbols and images. There's also some fish and birds that symbolize biodiversity. This is a book that was written by experts and edited by experts from around the world, from various institutions and international governmental and non-governmental organizations. I'd like to take this opportunity to also express my thanks for the translation into French by Professor Christian Rousseau, who really did an excellent job in setting up and developing this manual. So this book, which is called Mathematics for Actions and to Accompany Decision-Making with Science, gives examples of solutions to various social and environmental problems which use the help of science. It was written together with scientists and mathematicians from around the world. And it really illustrates the fantastic roles played by mathematics to confront the serious problems linked to the acceleration of global challenges. So this book is divided into different sections, but it's important to note that among the 17th Sustainable Development Goals adopted by the UN member states, 13 have been mentioned in this manual. So I decided to split them up in this shape where I explained, of which I've given you a quick overview of the contents. So there are questions linked to big data. As you know, especially since the pandemic, we have had to do several things. For example, using webinars and SMSs and online meetings, and all of these involve big data, billions and billions pieces of data. And in order to analyze this data, we need very advanced tools. And this book raises these questions and also allows decision makers to take stock of the situation in order to be able to confront this rapid growth of data, to be able to make decisions. Gender equality and its impact on the global economy is also an issue that's brought up here. Complex networks also brought up. Epidemiology, especially when it comes to the spread of disease, the study of how illnesses spread, infectious diseases, and so on and so forth. These are also things that have been taken into account in this book. And we've also very quickly explained the terminology used in the last years, things as flattening the curve, for example, when it comes to COVID-19. This is explained in the book. An explanation is given that is understandable by everyone. Resource management linked to climate change is another topic that is brought up in the book. Digital resilience is another point that is mentioned that different authors have brought up in the book. Since the pandemic has hit us, we have seen how useful digital technologies have been in everything that we do. So it is important to see how important resilience is in this field. But I don't have much time left, so I won't present everything that's in the book to you, but I'll just give you a quick overview that sums up what's hidden between its covers that I think should motivate anyone who's really interested in seeing what mathematics can do in the field of sustainable development goals adopted by the United Nations. So I will rapidly conclude my presentation, and I'd like to present the authors to you. They come from all over the world, and they are addressing themselves to decision makers as well as students. They are also speaking to teachers. They're speaking to all those who like, and even those who doubt, in the power of mathematics or the importance of mathematics in, or rather I'd say that they, when it comes to the usefulness of mathematics in everyday life. So that's what I wanted to share with you today. I don't think I was too long. Thank you very much.
Mohammed, thank you very much for the launch of the toolkit, the French version of the toolkit. Indeed, our aim is to make mathematics available for everyone in all languages. Now I would like to introduce you to our first keynote speaker for today, Dr. Patrice Horet. Dr. Patrice Horet is the research director of performances and mechanisms in Michelin. He has led the numerical solid mechanics group at the Michelin Technology Center and has coordinated academic and industrial cooperation in scientific computing and simulation. The main topics of interest of Dr. Horet are in the field of computational solid mechanics, ranging from the analysis of discretization methods to multi-scale and domain decompositions. In 2016, Dr. Patrice Horet was awarded the Felix Klein Prize by the European Mathematical Society. This prize is dedicated to young researchers under 38 years old who provide remarkable answers to concrete and difficult industrial problems. Dr. Horet, we are very happy to have you today, and the floor is yours.
Thank you very much, Amal, for your very kind introduction. It's a pleasure being with you today. Many thanks for your invitation. As you said, I'm in charge of a department today that is involved in the prediction of physical phenomena, the performance of our tires first, but also of other systems from the health sector to the membrane of hydrogen fuel cells. And so thanks again for inviting me, because I'm so attached to mathematics that couldn't be more at the core of today's challenges. So Jean-Charles, if you will, I can let you share the few slides that I've prepared. Wonderful, thank you so much. So you can pass directly to the second one. There would be four important messages that I would like to share along this presentation. The first one is that simulation has been playing a huge role in the design of products over the past 40 years, I would say, and will continue to do so with new products, new challenges for the decades to come. Secondly, data and artificial intelligence gain significant importance. It's especially the case through digital twins that open an avenue to the design of new products and services, and an avenue as well to new scientific developments as well. My third message would be about our collective sustainable ambition. And the sustainable ambition we work for is paved with amazing scientific challenges. And among those challenges, scientific and mathematical ones especially. Last but not least, mathematics is not only a language, it's not only a science, it's not only an asset for companies, it's also an heritage that really nourishes a living community. And I'll try to conclude my talk on this aspect. So you can pass to the first slide, Jean-Charles, if you will. Thank you so much. So there's an undeniable truth is that the fundamental laws of physics remain a privileged way to understand the mechanisms at all scales. And math, to some extent, intervene as the perfect toolkit, because not only math is the language in which those laws are written naturally, but they are also a way to determine accurately the solutions of these equations and to optimize the design of the systems. Indeed, the prediction of physical phenomena involves many scales, as is displayed on the slide, from the atom to the scale of the objects around us. And I will give one example close to me on the example of the tire design. It all starts with defining the best polymer and to understand the behaviors of the materials at the quantum scale. And indeed, we perform computation at this scale to perfectly understand how the chemistry will work, what will be the benefits of using such or such raw materials. Then comes the molecular scale, at which you start observing the dissipative phenomena, the adhesion between materials that are so important, that is so important when you build composite materials, composite objects. Then comes larger scales with the interaction between rubber, for instance, and the ground with all its details, and that creates the condition of friction. And then when you're done conceiving a tire, you still have to predict all of its performances: longevity, endurance, traction, rolling resistance, acoustics even, and handling as well, as you mount it on a car, or a plane, or every usage you can think of. And we do not only simulate how systems work, we always and also simulate the way we manufacture them. So you see that really mathematics, through the equations it resolves, operates from the smallest scale, the finest scales you can imagine, up to the coarsest ones. The job of math is to determine how accurate your prediction is. When you omit part of this physical modeling, I would say, it's also there to design algorithms so that supercomputers will provide you with accurate performance assessments. And ultimately, one would like to design the optimal tire, the optimal car, the optimal aircraft, the optimal systems that meets and maybe exceeds all of our requirements. The lighter, the most efficient, the most long-lasting, the most eco-friendly, you name it. And of course, everything I said on the example of the tire here applies to almost all industrial applications and almost all industrial devices. Now, let me switch to an important question, that is the importance of data. The importance of data is on the slide right afterwards. Wonderful. So, of course, as that was said before, we live in the era of data. Data openly shared by people in exchange of a service, data sent by connected objects all around us. And this data is absolutely key to understand how systems are used, to understand when they dysfunction, to provide users with some advice as well, and of course to suggest improvements for the next generation of objects you're conceiving. Not only data is interesting for new products and services, it is also helpful for manufacturing. On the central picture of the slide, you have an image of a factory. The information provided by all the machines in a connected way facilitates human interventions, predictive maintenance, as we call it, and all of that is what we call Industry 5.0, in the sense that data and artificial intelligence concur to a more friendly environment, a collaborative environment for people and workers in the plant. Still, despite the importance of data, in industry, quite often, the data is not as abundant as you would like, and sometimes it remains scarce. Why is it? Because any data you produce in industry requires that you build an object, requires that you multiply testing operations. And well, that's not totally for free. Another example, when you assemble a composite object, a composite system with pieces designed by various industrials, several companies, so not everybody is ready to share the data he or she has, because the companies want to keep a legitimate part in the value for themselves. And that's legitimate. And so data is not always as abundant as one would like. And so that's where simulation comes into play, because thanks to a combined use of data and simulation, you can get the best from both worlds. Simulation to provide the finest understanding possible of the ideal system, and data to retrieve the actual usage, to understand the gap between the ideal situation and what it is actually experienced in operation. This combination is very popular and is named as digital twin. Digital twins are there to allow real-time analysis, to provide accompaniment for the devices in use. Well, they have been first imagined by NASA quite some time ago during the space conquest, or the beginning of the space conquest, in order to steer a vehicle on a distant planet or satellite. A situation in which you cannot expect receiving all the information on Earth, make decision, and send the decision back to the vehicle. It's simply impossible. So digital twins are really there to find the best between the model you have, the simulation you have, and the data you discover in operation. On the slide, you have two other illustrations of the cooperation between data and simulation. The left one comes from my friend Dirk Hartmann at Siemens. It shows what could, well, be described as a virtual X-ray for a motor. It predicts the temperature field inside the engine based on external measurement and based on simulation. It's made to prevent failures and to stop, of course, the engine when the temperature increases too much. On the right side, you see the reconstruction of the blood flow in the aorta by simulation, taking benefit from medical imaging. So all of that is to let you apprehend all the benefits that comes when data and simulation actually meet. My third slide on new challenges will be coming. If you were Jean-Charles, wonderful, thank you so much. We at Michelin commit for fully sustainable tires by 2050, and we are already on a very good way. And working for a sustainable world implies many challenges, and I guess that the other speakers will maybe mention some of them. Among these challenges, boosting the emergence of sustainable materials, understanding the natural degradation of materials, identifying recycling opportunities, assess carbon impact, model carbon capture, and unveiling green energy sources, which are so important. And in all of these challenges, there is mathematics to assess human impacts and to design alternatives. Two examples actually on the slide. On the left, you see the interaction between a polymeric material and an enzyme that is degrading it. It is a simulation that runs at the molecular level and fosters tons of questions in which math have a key role to play. What are the byproducts of the degradation? How you can simulate them? How could they be used? What are the possible options to recycle? Are there better enzymes to do the job? Are you, by simulation, able to design them? On the right of the slide, you see another example. That's the simulation of the membrane in a hydrogen fuel cell in order to understand the impact of the materials in the performance of the cell, its proton conductivity, so as to speak, And it's an example on the path of to greener energies, which is of course a key challenge. I'll finish my intervention by speaking of mathematics at large. That would be my last slide. So mathematics is definitely the common language for predictive sciences and quantitative assessments. It's an asset for companies because we never have enough mathematicians in the revolutions that are taking place. Mathematics really foster interactions in this changing world. They're an incredible occasion of public-private partnerships worldwide. And I'm mentioning on the slide a number of I would say, associations and scientific societies I've been involved in Europe. And I would be citing UMatin or AMIES in France that do a fantastic job to gather private and public interests and to take the best out of mathematics. Mathematics drive countless challenges: data analytics and artificial intelligence, complex systems handling. And in this changing turn of events, it's an occasion for mathematicians to deepen their relationship to other fields, which are sources and will be sources of stunning problems. All over the world, that's what I was saying, scientific networks really do a great job strengthening their link to industry, to education, to public policies. And I will not mention them all, but they will recognize themselves. So thank you so much again.
Thank you very much, Patrice, for taking us through this beautiful journey of using mathematics in important industrial applications. Thank you very much.
You're so welcome.
So now, next, I would like to introduce you to a young researcher, our second keynote speaker for today, Professor Olga Fink. Professor Fink received a diploma degree in industrial engineering from Hamburg University of Technology in 2008 and the PhD degree from ETH Zurich in 2014. She has been an assistant professor of intelligent maintenance and operations system in APFL since March 2022, and her research focuses on hybrid algorithms fusing physics-based models and deep learning algorithms. Hybrid operational digital twins, transfer learning, self-supervised learning, deep reinforcement learning, and multi-agent systems for intelligent maintenance, and also operations of infrastructure and complex assets. She has gained valuable industrial experience as a reliability engineer for railway rolling stock and as a reliability and maintenance expert for railway systems. Since 2018, Professor Fink was awarded, actually in 2018, she was awarded the prestigious professorship grant of the Swiss National Science Foundation. Dear Professor Fink, it's a pleasure having you here, and the floor is yours.
Thank you very much, Amal, for the very kind introduction. Also, thank you very much for the invitation. It's really a great pleasure to be here, and I think it's the most international audience that I ever had so far. So thank you very much for joining and for your interest. And in fact, I actually decided to show you one of the examples on the projects that we have been working on, since we are typically collaborating with industrial partners to demonstrate how the algorithms that we have been developing can be also applied in the applications. And the example that I have chosen is actually not connected it will be connected to a complex system. But the idea is actually, how can we learn from domain experts, then distill their knowledge into an algorithm, and then use that algorithm then to support decision makers afterwards. So that's the focus of the presentation, and will be shown in a particular example. So what we are normally dealing with and what we are concerned with is to detect faults. And on this kind of such a rather simple example of a railway wheel, we are interested to detect if there is some abnormality in the wheel. But not only that, we're also interested to be able to distinguish between different fault types. And in this case, it would be a flat spot or a non-roundness. So we need to distinguish between them as well. And once we detected the non-roundness, for example, we are interested in how this evolves over time and when does it really reach a critical point. And this is where we would then like to perform predictive maintenance. So we would then try to avoid this and to schedule maintenance before the fault is actually happening. But if we know how the system condition is evolving over time, what we actually can do with the information is we can start applying or prescribing how the system should be rather operated in order to prolong the remaining useful lifetime. So we're acting more proactively, so not just scheduling to replace the component, but rather prescribing how it should be operated and then really applying this in real time and in a more proactive way. So this was just for the introduction of some of the terms, since the talk has also been called on predictive maintenance. And the system that I wanted to discuss with you a bit today, or in the example, is actually one of those tunnel boring machines. And given the progress of a lot of tunnels that have been bored for road or for railway tunnels, for example, the application has been really massively progressing. And one of the challenges with them is really this high uncertainty due to the geological conditions. So even though there may be some samples taken before the project is starting, once the project is underway, there will be a huge uncertainty about which geological conditions the machine is actually encountering right now. And this really results in high uncertainty for cost, but also time overruns. And this is really not quite common in this very big tunnel constructing project where the cost and the budget and also the time is quite often overrun as well. And obviously there's also some safety critical risks that are linked to this as well. But one of the interesting observations of the operators was that they observed that in different shifts, different operators had kind of really different progress rates that they were able to manage. So there were obviously some operators that were really good in kind of setting the parameters based on their experience in such a way that during their shift, the progress rate would be quite high. And then some others were less experienced, so the parameter settings that they did was not leading to the same progress compared to the more experienced ones. And the question was actually, how can we really leverage the experience and the expertise of the domain experts? And one of the challenges that we are facing here is that it's actually quite difficult to even quantify how good their decisions or the parameters that they were setting up is. Because the same parameters under very different geological conditions will really result in very different progress rates. So this is really quite difficult to distinguish between those two, because there is no formal parameter quantifying how good those operators actually were. And if you look into their current tunnel boring machine projects, what is really happening quite a lot, and this has been also already mentioned by the talk before me, is that a lot of systems are currently being equipped with a lot of different sensing mechanisms, and this is the same is true also for tunnel boring machines. So they've been equipped with different sensor devices. So they're really collecting quite a lot of information on the condition. Just to give some examples, it's the torque, the rotational speed, the thrust, just to the parameters that are measured, but also many additionals as well. And the question that we are facing here was, can we really collect sufficient data actually to learn from this data, and then really to develop algorithms that we are able to distill this domain expertise and then to give it back to operators as well. And we were actually quite lucky. So we had a case study with our industrial project partner where we had 6 microtunnels that were bored in very close neighborhood, which is rather seldom to do, seldom that it occurs. And it was rather not the big one that I was showing you. So it's a small diameter with about half a meter. So normally this is where it's used for cables, for example. And another kind of lucky condition for this project was that the project was also accompanying by geologists. So geologists were there, and then they were taking their information, the geology, and then we were trying to record which geological profile was now encountered by these machines. And this led us then to develop kind of the 3-step algorithm. And obviously in the first step, as always, and it is very well known, we need first to collect the data, but also to pre-process it as well. And collect the data is also to get information on the different geological profiles. And we only particularly looked into the homogeneous profiles because these were a bit easier for us to handle. And we collected this quite a lot of sensor measurement data that we then started to pre-process. And as those of you who are working with industrial data, there is quite a lot of pre-processing that is really required. So we, for example, needed to remove some of the transient sections. We needed to smooth the data. Unfortunately, when all the cleaning ended, there was much less data left than we actually expected. So this was a bit of a disappointing point, but we still continue to work further on it. And now comes actually the core of what we were aiming to do. So the first step, what we needed to do is actually to be able to quantify how good the operating parameters are. So the control parameters are that the operator set. And obviously what is relevant for us is the advance rate. So, and then, well, it's not the higher the better, but we observe kind of the maximal one, and then we put it into relationship to this advance rate. But what is also relevant, or a second relevant parameter to monitor, and this is also monitored by the control system of the machine, is the working pressure. And there is an upper bound that is really set, and once the machine reaches this upper bound, the machine is just shut down. And we don't want, and then we need to restart, which takes really quite some time. So we didn't want to reach this upper bound, so we defined a second marginal bound, and then we penalized if our working pressure was coming close to it. So this is why we have 2 terms, but if we are far away from this marginal bound, we did not penalize it additionally. So with this, our target was at least defined, and then we could tell we normalize it to be between 0 and 100 just to make it more interpretable. And then came the second step of the algorithm. We trained the algorithm with a neural network. And those of you who are familiar with neural networks, so there is no magic behind it. It's just simple computations that are performed. So we have the inputs that we take, we multiply them with the weights, we apply an activation function, and then we perform it step by step until we reach our target value. And once we reached our target value, we compute it with the ground truth information. We then compute the loss function, and based on that, we compute the derivatives, and then we adapt them in a way, we adapt our weights in the way so that in the next forward pass, our target value will be much closer to the ground truth information. So that's just the information, how it's computed, but basically it's a neural network where we took the control parameters, the context parameters, and our target value was the optimality. So this is how it looked like. It follows it quite nicely, but it's also not very precise. But this is just informative value, so we didn't want to have it very precise. But at the end, we were not interested in predicting the optimality. This is kind of one of the additional information that we do desire. But what we actually wanted to have is how to adjust our control parameters in order to improve this optimality. And now we kind of went back to this idea of the gradient. And the idea of the gradient is how do we adjust our parameters in order to improve it? And this is basically what we do. So we first train it, then we fix the weights. And once the weights are actually fixed, we are then taking a first order derivative of the model output with respect to our control parameters. And this is a subset of our input parameters. And this then provides us information on how to modify these control parameters in order to improve the optimality. And it's kind of a very intuitive way to do, and also very straightforward. So this is what we are then able to do. So on the one hand, we are providing this optimality parameter, given all our input parameters. We are then computing the gradients. We are providing recommendation for each of the control parameters. So for example, increase rotational speed and decrease thrust. But on the other hand, what we also need to provide is how certain the algorithm actually is on the recommendation that it's provided. And we called it credibility, and it's actually combining two different types of information. On the one hand, we are looking into how well was the algorithm able to predict the optimality in the close neighborhood of this observation. But on the other hand, what we're also considering is how good were their, or how close were their, how good were the actions that were taken under very similar operating conditions. And then we compare them. We also compute the weighted average over a number of neighbors, which we set to 15, and then we compute a credibility number. And this is, for example, 83% credibility. And with that, we're actually set to go. So on the one hand, we need to know the ground class information because we have this algorithm for each ground class independently. We then have the sensor recordings that we are feeding in. We now know what the optimality is. We provide recommendation for the different control parameters, and we also let them know what the credibility actually is. And the algorithm can be applied in parallel to their to the normal operation because we are currently not allowed to go inside the control system. And there's still some challenges that we need to address, such as data scarcity, also uncertainty, and of the geological conditions. But also we actually did not have access to the real operator actions. We needed to derive them manually. And that's basically it. With that, I would like to end. I would like to thank to my amazing team, but also to our industrial collaboration partners, to our funding agencies. And if you have any questions, either type into the chat or reach out to me by my email address at EPFL. It's easy to find. And thank you very much for your attention and for the invitation as well.
Thank you very much, Olga, for this great presentation. Thank you so much for that. I am now pleased to hand over to Professor Christoph Ritzinsala, who will be moderating the panel discussion, which will be about mathematical innovations for sustainable industrial systems. Professor Ritzinsala is the Executive Director of the International Center for Pure and Applied Mathematics. This center is based in Nice, France. It has a mission to promote research in mathematics in developing countries. And to date, SIMBA has organized 340 schools in 62 countries. Dear Christoph, thank you very much for being here with us today to moderate this panel discussion. The floor is yours.
Hi, thanks a lot, Amal, and thanks a lot to UNESCO for organizing this very nice event. And I also want, of course, to thank Jing Zhao for her kind assistance with all the technicals. So yeah, I guess happy Pi Day to all of us first. And as I said, I'm really happy to be here. And I have like 3 panelists today with me to help maybe trying to make a bit clearer what is industrial mathematics. I mean, we have seen like 2 talks about it, but maybe it's not clear to everyone how it works, and also maybe you have some questions on how the interactions with industry are when you are a mathematician. So the 3 people who are going to be with me today, so it's Étienne de Roquigny, who is founder of Blaise Pascal Advisors and former Deputy Dean of Research Central Paris. Then I have also Claudia Zagasti-Zabal, who is an independent researcher associated with Unicamp and SEMAI, so in Brazil, near Sao Paulo. And finally, Professor Fatma Zohra Nouri from Badji Moka University, in Algeria. Thanks to the three of you for being here with me today. So we have roughly half an hour. I prepared a few questions, so feel free to, if you want to intervene on some of them or on all of them, you let me know. So first, maybe it's because we are mathematicians, but the words industrial mathematics, they kind of speak for themselves, but it might be good to try to make them a bit more precise in the way how you would distinguish industrial mathematics from pure or applied mathematics, and how also you would work. I mean, for instance, when you're industrial mathematicians, do you work at a university? Do you work inside a company? Are you free to choose your topics? Can you publish all your results? Do you work with technicians? Are proof important for you, or are they secondary with respect to the results that you shall get? Yeah, maybe we can start with Claudia on this topic.
Sure. Thank you, Christophe. Hello, everybody. Very nice being here celebrating math. I enjoy a lot the presentation so far. I always say when you do industrial math, a difference with respect to purely academic or applied mathematics is that in the academic world, you are done with your research after it's published. It's the peers that have evaluated it, and then it is finished. When you do industrial math, there is one step forward, and it's that the counterpart, the industrial counterpart, uses your algorithm and puts it in practice, and this exposes all of a sudden a lot of potential weaknesses or extensions that you had not thought of when you created this innovation. So it is very enriching for a mathematician to do this step, to traverse what it is called the valley of death in the area of transfer of technology, where you have your mathematics is good for that also. You have a technology level of readiness that is relatively low for it to be included in a company. And then there is all this when you are in the academia. And then when you have to transfer this to a company and it has to start being used constantly and has to be reliable, then there is all this path. This is what is called the valley of death in this area. And then industrial mathematics is there. It's in this valley of death, making the bridge between academia and industrial. So it's very rich, it's very exciting. I have done all my career in this valley of death. And so it is good for the scientific point of view. But another thing is that proofs are important. Of course, they are important because they ensure that the result that you obtain will be able to be reproduced with different sets of data and so on. And that is important. It's not an opinion. It is a theorem. It is a statement. And this kind of solid guarantee of reproducibility, it's important, and it's important contribution of mathematics to this area.
Thanks. Fatma, would you like to add something? We can't hear you. You have to switch on your microphone. Fatma, we can't hear you.
It's my sound. So I would say industrial mathematics is a branch of applied mathematics, while applied mathematics is more or less theoretical simulations for typical problems like in biology or theoretical physics or in experimental sciences, while this branch of industrial mathematics are more or less dealing with a real industrial problem where we are looking for optimal solutions in a very, how to say, un temps record, a very real time. So I think industrial mathematics are requiring more effort to get really real solutions for real problems. I would say, for example, if we're looking for how to optimize production of oil or gas, we need really, how to say, big data, real data. While in applied mathematics, we only deal with maybe less data to give the model and the solution, and also using the methods related to that. So I think industrial mathematics is something to do with the economy, big economy.
So you would say what industrial mathematicians gain for this confrontation is the fact you have like real data to work on?
Yeah, and the big data.
And
really
large amount of data. Okay.
Large. So although it's a branch of applied mathematics, but still needs more effort, whether in theoretical mathematics, in the analysis, in the numerical analysis, or the simulation, the algorithms, because they seem to be quite complex problems.
Mm-hmm. And in this fast process, as you mentioned, that is needed somehow, do you need to compromise about the importance of the proofs, or are you still having the impression to do like a mathematician job?
Yeah, I always say I have been part of some study groups in industrial mathematics and mathematics and industry. Yes, for the people who present the problems to us, whether from the oil companies or else, they don't seem to give importance to the theoretical behind the model, but we do. The mathematicians, we have to deal from the theory up to the results, because to choose the right method, we have to analyze the problem first mathematically, and to do the simulation, you have to do the numerical analysis in the analysis part of it that would lead you to choose the right discretization parameters, and then to get a good result. When I say good result, it should be stable, because we cannot just take the problem and put it in the computer to get the results. You have to do the whole, that's from the mathematics to the applied mathematics to the computing simulation.
Yeah, thanks. This is very clear. Maybe for the three of you, I mean, to try also maybe to see what kind of mathematics you do or how you work with industry. May I ask what is the best or the most interesting contribution you had in this domain so far? And maybe I can start with Etienne.
Yes, thank you very much, Christophe. First of all,
we can't
I will just add a last comment to the previous discussion. Sure. About entrepreneurial mathematics, because myself, I'm half mathematician, half entrepreneur, and my business is to set up big businesses with math. And the good news is that math are very creative, just as creative are entrepreneurs, and it's a really very exciting match. And today is a period of great entrepreneurial successes and great math. And we all know those big companies, GAFAM, are essentially applied math companies. And so this is a time for entrepreneurs and mathematicians to work together. And I'm also pleased to share the name by which my own company is named, Blaise Pascal, who was, many people know Blaise Pascal as a philosopher, and he was also, of course, a mathematician. He co-invented probabilities and also integration and many other things. But it's less known that Pascal was also a big entrepreneur. He set up big companies using math. He invented Uber in the 17th century, and he did also entrepreneurial ventures in agriculture. So he set the way for what we have to do today is to create meaningful companies, incorporating math and also entrepreneurs and also good philosophy to have good impact. So now maybe I'll give you two examples of which I'm particularly proud of, mathematical ventures that are growing now. Two different companies helped by my own company. Now, the first one, our big challenge is decarbonizing buildings. Now, some of you may know that those buildings, through heating, ventilation, air conditioning, contribute a massive amount of carbon emissions. And so the purpose of our company is actually to decarbonize up to 90% the carbon emitted by a building through heating, ventilation, and air conditioning. We do that combining photovoltaics, geothermal energy storage, and of course, a clear understanding of the energy needs. And we need a whole stack of applied math there. We need to mix all together numerical modeling of the subsurface, also of the building. We need also to do machine learning to understand the energy needs, which are always evolving. We need also weather forecast, and then we need operations research. We do stochastic optimization. We do optimal control theory, and we all do this in a sort of a robust probability context, because we actually our company, which is called Accenta, you can check on the web, accenta.ai. We actually commit ourselves during 20 years to reach a certain amount of CO2 reduction. That means if we don't reach that amount, we will lose a lot of money. And if you want to be sure about something, you need to do math, not only modeling, not only machine learning, not only coding, you need to do math. And for me, that's the big difference between computing or modeling and math. Math is about being sure of properties of the system and having certain bounds within which operation will be guaranteed. And that's very important if we want to meet those carbon reduction objectives. And for our company, it's a key financial asset to be able to control that. And for that, we really need mathematicians, not only just computer scientists and all those kind of data scientists that everyone wants to do data science. Now, we need to have people that are also able to understand likelihood estimation, a robust bound on estimates, and also understand in what kind of geometry you can actually be sure of the optimization results and not fall into a secondary and all the theory you know. So we need these kind of mathematicians, but of course those mathematicians can only be helpful if they are working in very close teams with physicists, engineers, and who also code. So this is the kind of, for me, entrepreneur mathematicians we need, is those that have a large culture in mathematics, not just in numerical modeling and not just in machine learning, and many different branches altogether. And they're able to discuss and work with field engineers and to code, and they're motivated by new ventures.
Okay, maybe before you move to your second example, let me maybe switch to Claudia first.
Okay, thank you. Well, my personal experience is mostly related to the energy sector. And in that area, what I consider is my most important industrial contribution is relative to pricing the energy, how much it will cost for a system that produces energy to produce 1 more megawatt per hour, because we all like being here having electricity, and the electricity needs to be distributed through the network. And we don't know much how to store energy once it is produced, because batteries are small. But what we do know is how to store energy in the form of water in the reservoirs, in dams, right? This is the way we have in all the countries to store energy. My PhD work, after 10 years of being tested inside Electricité de France, is part of the program that for 20 years has been used to determine these kind of values for deciding which type of technology will produce what, if it is fossil fuel, less and less now, or some sustainable source of energy. So this brings me to the current problem that we have been trying to solve in Brazil, that is mostly green in terms of producing energy, that is referred to, if you use water to generate energy, this means that you will not be burning some fossil fuel, which is what is desirable. But on the other hand, if it doesn't rain, you will not have water in the future, and you may have to burn more fossil fuel, and it will be more expensive. This means that we need to find sound ways of assigning value to this stock of water, to water that is free. Rain is free, but it's not free in terms of value. It has a lot of value. And regarding sustainability, now we have to take into account multiple uses of water. What is the value of the water that goes inside of a strawberry that is being exported in a region that is dry, right? Where there is this value that needs to be taken into account. And mathematics and the kind of mathematics we do relative to optimization, stochastic optimization, can bring an answer to that. So, well, this is the area where I feel I have done more contributions and most proud of.
Yeah, indeed. Thanks. Fatma, you would like to add something?
Okay, I just put it on. Study groups of mathematics in industry, so I gained a lot. I understand more, what people need from mathematicians. So people come and present their problems, purely industrial, a lot of parameters, and you have to deal with that and then combine to find the model. And we're always rushing to find a good graph or a good numerical result. But I always start because I started my career as a pure mathematician. I have to look deeply in the analysis, see whether or not the problem is well posed or not. If it's not, I have to find the right tools, mathematical tools to regularize it or get a better. Well, when we are modeling, actually, it's not the model; it's just one model, which is not. So find the optimality of that. That's for example, once there was a study group which was organized in Annaba from the factory of steel, because the big factory of steel in Algeria is in Annaba. And it was an international study group, and Oxford University was a partner for that. And we learned a lot from all these problems. So what they do actually nowadays, they control the defect of the product of steel, for example, by computers. And this is via an image. And since 2008, I think I started to work on image processing by PDEs, by partial differential equations, or by mathematical tools, whether wavelets or other. And we can say, by analyzing these images from the factory or from the industry, we can say it's a defect or something else, because we can look at contours. It's a large topic on that. And another experience is another study group was organized in Saudi Arabia in the coast. And then the people came with the big data from Ukraine. And we are looking at how to optimize the production of whether oil or gas by mathematical also modeling. And via the model, which is really good in that, where of course there's the mathematical model, the analysis, the numerical side of that. These optimization techniques would also direct them how to dig all these wells. I mean, it's amazing. So nowadays they dig horizontally, not vertically. Yeah, because we're looking on all this data, trying to, knock out one or two wells and look on a set of, a number of wells, and then we are choosing which one from the data, of course, which one are more predictive or not. And then we were saying, okay, maybe we don't know it and we're not engineers, but maybe you need for maintenance to knock out one of them. And they were very happy. It's just maybe a naive discussion from a mathematician, but they will direct them. They will, it's this exchange. I mean, the terminology is different, but the goal is the same.
I see.
Yeah,
Well,
it's time to work together, I think, as a mathematician or engineers or industrials, because this exchange of terminology will lead us to better, to find a better way or better solutions, optimal solutions.
I'm just trying to move a bit to the next topics. I'm sorry, Etienne. I mean, maybe we can keep the second example for the question and answer session. I mean, time is flying. We started 10 minutes later, so you allow me to go to 25. Thanks, Amal. Yeah, so you mentioned like a bunch of topics. I mean, like price from electricity, and like now you have like oil companies. Somehow, I mean, from my point of view, it shall raise at some point also some ethical questions, right? I mean, when you're going to deal with company, you can't be just like when you do math saying, I mean, I'm just doing science, what it is going to be used for, I'm not really concerned. I mean, this is already like a kind of philosophical position which can be contested, but now you're going to work on a specific topic. So how do you deal with the ethical behind? And do you have all the data also to know how this is going to be used? Well, maybe Etienne, you want to tell us something about this?
Yes, I think ethics is a very big topic for us industrial mathematics, because first of all, if you want to have people working for you in the long term, they have to find a deep meaning in their work. And there is nothing worse as an ethical scandal to move people out of a field. And I think ethics is a nice opportunity for mathematicians, because in to a large extent, ethics is about first transparency, is about understanding what's underway. What kind of prediction am I doing? Why am I doing that kind of prediction? On what kind of data I am working? What are the characteristics of those data? And how does the algorithm perform in terms of dependency between the input and output parameters? And is that relationship fair? Is it fair? Is it working in the way it should be, in the sense of justice? And I think in that respect, there's also a big difference between, let's say, computer scientists who do big machines that perform magics, but no one really understands how it works, and mathematicians who should be those helping set the clear properties and set up confidence on why the system is behaving that way, and the geometry of data, what kind of confidence we can have on the relationship, what kind of risk we have, to what extent those risks have some weight. So all those questions are mathematical questions, and in many cases, more mathematicians would allow the way to more ethics. And maybe I'll talk about my second example. When we're working on geotechnics, and we've seen in Turkey with that awful earthquake, so many casualties, so many people who died. And of course, as the professor showed before, there's a lot of uncertainty under the soil. You don't know exactly how the soil actually behaves. And there's not enough transparency in the way that codes of buildings are being developed. And another venture I have with a company which is called Fondasol is actually getting all the data you can have on the soil, exposing this in a clear way to understand what are the characteristics of soil, and with the help of both machine learning and probabilistic mechanics, to what extent can you be sure that your building will hold? And is there some kind of cheating in the codes you have? So bringing transparency so that people can understand what kind of properties they have. I think this is a big challenge, crossing ethics and applying mathematics.
Yeah, this was indeed a very good example. Yeah, thanks a lot. I will share at some point, there is a nice study that has been made on industrial mathematics on the point of view of a sociologist. I'm going to share the link in the chat. And at some point, what you said about artificial intelligence being about control, it ring a bell, because she exactly wrote that artificial intelligence is about controlling when mathematics is about understanding. And I think that's a very good comparison to make. Maybe, Claudia, do you want to say something about the ethical part, but like very shortly, maybe 1 minute, so we can switch to another topic?
Okay, so let's start. I have seen a shift in the regarding secrecy. This is my experience in the last 30 years with big companies like Gaz de France or Électricité de France. It was impossible to get some prototype to work with. We had to go to the company and make corrections with somebody in the back in the code to see if things were not transgressing some of their privacy rules. While now all this has become, all these open source codes and all that is a culture that is also has arrived in the companies when they, in many companies, not all of them, of course, when they deal with academia. So this has facilitated a lot our work, because I think it's our responsibility when we establish an industrial collaboration to make sure that our PhD who work on that will afterwards get a publication, for example, because for finding a job, this is important. So I have seen this change and I welcome it. And regarding data, this is the most important thing to put in a contract from the academic point of view is without having access to a prototype that it can be worked, and with data, sufficient data, the project cannot move forward. Thank you.
Thanks. Yeah, and Fatma, do you have also something to add?
Yeah, very quickly, I agree with Etienne. I understand the security reasons for the governments, but it's about time for us as researchers to convince all these governments. And the two big examples is the earthquakes or the disaster, the COVID. I mean, since the COVID, we have more open source data from medicine, while before, the only thing I've seen in my life is when I participate in the study groups, whether maths in medicine or pharmacology. I was very happy to have all this amount of data, which I use it, and I have to be very secretly. I mean, I don't want to put it, to give it to anybody. But it's still, we still really don't have enough data, even from my country. I'm just next door to the factory of steel, but the only thing I get is from personal contacts for my PhD students, not for research. If the journal from where we publish, they ask for the data, I'm not allowed to give it because I got it from somebody as a personal contact. That's all I can say. I understand the security, but it's about time to convince our governments to let us, I mean, at least use for research.
I see. Yeah, I understand. I mean, of course, I mean, relations between like the mathematical community and the industry are frictional in the sense that, I mean, we work with different reasons sometimes and with different pace, and finding the right ground to compromise might be delicate. And I guess also the way to do it is maybe to have like someone who has already some experience. I don't know. I mean, maybe I will ask just Claudia and Fatma about that. How was your first time, Sama? How did you get introduced to the world of industrial maths? By someone, by coincidence?
That's a good question. Yeah, the first time was I'm heading a master degree, which is differential equations and scientific computation. And my students need to have a training in the industry. Naively, I sent them to somewhere next door, which is the factory of steel. and also the Center of Research in Metallurgy and Mine. And there, the director was a very good scientist, I would say, and he loves mathematics. And then the relation has started from there. And we got some images from the steel. That's how we started the image processing there. And instead of working on any image, like any synthetic image, we started working on a real one. And we found very good analysis on mass. We found very good results. And he was really proud of that. He was the director of the research community there. And then now he is supervising PhD students with me on real industrial problems. And from there, he can provide the data for us. That's how it starts. Maybe I don't know, from first contact, and it becomes a personal contact, and then we're working together as a team.
Okay,
That's
Claudia,
my experience.
you have a similar experience, or?
For me, it was perhaps something similar to a SIMPA school. Many years, yeah. In the 90s, there were a bunch of researchers that were mounting the European Consortium of Mathematics in Industry, headed by Helmut Neunzert. And they came to Argentina, where I am from, and they show the kind of things that could be done. And then I tried to study those things. And then when I went to France, I was lucky enough to go to INRIA and work with Claude de Maréchal, who was working with Électricité de France for many, many years. So I was lucky, I would say.
Okay. So coincidence more, okay.
Mm-hmm.
So we reached the end of the roundtable session, but we have 15 minutes more, like somehow for question and answer. So there was one question that was asked in the chat. So so it's for the three of you, of course. How can we start attracting industries to open up with mathematicians from academia for us to develop industrial maths in our department? Would like to say something about that. Okay, Claudia.
Thank you. The study groups that Fatma has mentioned many times are fantastic for that. It's a very good way. But my more pragmatic advice is accept to co-advise masters and PhD thesis with engineers and computer scientists or physicists, people from other areas that are not in mathematics only. Accept to do that. And then that creates, I have seen that alone. I have been doing that for more than 20 years, and then mostly with electric engineers, because it's what I do most. And then that you transmit this way of thinking a problem that comes from mathematics that is very structured and reproducible, and that, well, we have mentioned all these features. And then it gets into these students that later on become perhaps like Patrice Auré, heads in their companies. And when they will have a problem, they will come to you. This happens constantly to me now after 20 years of planting. It's not immediate, but it's promote interdisciplinary studies. Don't be scared of that.
And Patrice also mentioned in his talk some like institutions that can help, like trying to make the links a bit more formal, or at least quicker, I mean, or more visible, at least on the web for industry. So, I mean, yeah, he gave a bunch of examples, like Amiens, for instance, in France is a good one. Etienne,
if I can afford a comment, so thanks for the question, and thanks also for the answers, Claudia. I think it's some extent is very much of a reality, but of course it takes people at the interface that develop a specific sensitivity from the part of the lab as much as from the part of the industries, and it's all of a question of meeting the right people with the right intention and the intention to collaborate. But that sounds very real to me already. So I guess that one of the reasons why we are all here today is because we've experienced that in the richness of these public-private collaborations on the long run. So you just have to make it happen.
Fatma or Etienne, do you want to say a bit more about?
Yeah, it's true. I think wherever we are, I mean, I'm in Algeria, my colleagues are elsewhere, and we have all the same experiences. But there is something very positive I would say to all my colleagues present here is December 2021, I was really, how to say, astonished when La Sonatrach, which is a big company, that's the economy of Algeria, came to its University of Annaba, where I am, and they wanted to organize a workshop between the scientists, academicians. So they have chosen some national projects because they had to look at the projects. And I was one of the people who was invited because I was working on problems related to oil. They've seen all the theses online and everything, and they invited us. That was my dream. I was fighting for a long time. How can I approach? They always accept the computer science people rather than us, whether mathematics can code also very well. And then we present, I mean, mathematics can code as well. I think mathematics is only pure and everything. When we present all the work we have done, that's from the black oil model up to saying to them it was a very bad model, and now we have to go to something else because the medium is not the same whether you're in Algeria or somewhere, and it's not the same. We have to look at the media first, whether it's spurious, whether it's sand and everything. And we were accepted. I mean, there are people from chemistry, from the physics, from the mathematics department. So how to say, the communication was very well set up. And that now the government, I mean, the big Ministry of Higher Education and the industrial one are trying to find a way to put the commission between the two, and we can put up some projects between industry and academicians. That's university.
Let me ask also, is there even in your courses, let's say at master level, some courses that are oriented to industrial math, or I mean, it's more like when you have to reach a PhD to start having like some interaction.
No, even the master degree, it's the only master in Algeria I'm leading with. I mean, the first year is pure, I mean, the first semester is pure math. The second one will be methods and application. And the third semester, which you see 2 years, it's really applied mathematics, where we look at oil problems, image processing, medical science problems, and also now we are doing some stochastic studies because the determinist one didn't give a lot. And they have 1 month at least as a training in the industry with the Sonatrach. So they are, I mean, the university had also put up some convention between the two, and the students go and learn a lot of things from practice. And then the subject of the dissertation would be related to what they have done as training, which helps a lot. And one good thing also, they can also offer jobs for master students. I have 2 students who are already, which is a positive way for the government itself.
So I think that answers another question in the chat. I mean, where some people were wondering if there are scholarships to study industrial mathematics. So you somehow gave an answer to that. And Etienne, you wanted to add something.
Yeah, I want to be let's be very clear. We have a big problem with the time constant, right? So there is one time constant, which is rather traditional in industrial mathematics. You count in years. So you start a collaboration with a company and it takes 6 months to understand. Then you set up a postdoc, whatever, a PhD, and it takes 1, 2, 3 years to have some satisfactory results. Now that's one category. Now that category is nice, but no way you can attract entrepreneurs. If you want to attract entrepreneurs, the time constant should be in weeks or maybe in months. So the key question here is what can you truly afford as a researcher? Can you afford a time constant in years, and then you go to industries who can wait for years before having results? Or are you ready to go into more agile startups or scale-ups? And then you have to be prepared to react in terms of weeks and months. And so the two, for me, there are good maths in the two categories, but it's quite different. Now, of course, now I used to be at Électricité France myself also, and then at Centrale. I used to work in years, and you can do some great industrial mathematics. Now I'm more into this entrepreneurial world, which is full of great math also. But you have to be ready, you have to organize yourself in order to be able to answer in weeks and months. And you also have to work in a problem-solving attitude, which is different from the rather, let's say, set up hypotheses, put equations, and then solve a mathematical problem. You have more to be into a problem-solving thing. And for example, you should be able, at the end of the first meeting, to write in 3 equations the essence of the problem, and then try to solve this after the first meeting. And I can assure you this is possible. And this is also very creative and very exciting. Now it's those are different ways. And if you're ready to do that, then there's great opportunities. And of course, that world of startup scale-ups have a lot of money. And apart from SVB failure earlier this week, but so they're ready to work with math because they have big mathematical problems. But you have to organize yourself to answer with that time constant.
And this is interesting. I mean, because it's typically one question which is at the core of this report I put in the chat, discussing indeed if one can do mathematics on very short delay. And also, I understand that there can be a debate around that. I read that the common opinion of the mathematicians were that they would not go for short delay problems because, that's not how mathematics works. If you can really give a solution in 1 week, it was not an interesting problem at the end.
No, I was not saying giving a solution in 1 week. I was saying that you are ready to model the problem, to set up the problem after just 1 or 2 meetings, not meaning solving the problem, but already setting the problem is a very important step because that step guarantees that there is some clear understanding of what we're talking about. And then because I did 20 years of collaboration between industry and academia with different roles. And in many cases, we lose months, if not years, with misunderstanding. We understood that we had to do that, but as a matter of fact, it's not interesting for us. So you've developed nice math, but it's not answering our industrial stakes. So, and that's a big cause of failure of this kind of collaboration is misunderstanding of the goals and of the clear setting of the problem. Now, once the problem is set, okay, it may take years to solve it in a full property proof way. Okay, now sometimes when you've well set the problem, you can have some heuristics in the first month, and then you will prove it. Like Fermat, it took four centuries to prove the Fermat heuristics, but it didn't take years for Fermat to issue his heuristics. So heuristics usually take less time, and it's already useful. So yeah, I don't know if I understood your question.
No. I mean, yeah. You made your point clear. Yeah. We have a bit more question in the chat. I mean, people are quite interested in the ethical implications. And so there was a question about political implications, like political pressures, dual use. I think we are going through near conspiracy theory or things like this. I don't know. I mean, did you receive any political pressure at some point in your career? Any of the three of you?
Pressure.
No, it doesn't seem so. No pressure.
Oh, no. I think we had maybe not open doors because there was no communication from the beginning. But once you start, once the other side will know you, Maybe Etienne was very clear about that. And you have to put a good framework from the beginning, and you have to be convincing, like politics, exactly what we understand about. Because the other side in the industry, there are a lot of security and things that they don't accept very easily people coming in and just propose things. But once the framework is set and the communication both sides is set, I think things will be easier. It's the, I don't know how to say, la confiance between the two.
The trust, yeah.
And also what we do is we support decision making. We are not in the decision process itself, right? So I often joke and I say, what we provide is used to blame if something goes wrong, but we are not giving credit if something goes right? It's, it is support the decision making. We are not decision makers.
Well, to some extent, as entrepreneur, I'm a decision maker, and in my own garden, I can already make.
Talking about politics.
Yeah, but I think it's sometimes there's this temptation to set all the evil on those big politicians that are above us and that control everything. Okay, to some extent, yes. But we can already do a lot at our scale. And once again, I really think that mathematicians have a great role in establishing trust and starting with a clear formulation of the issues. Now, putting things in equations is a way to clearly formulate what those things are about and dissipating some misunderstanding. And in the life, misunderstanding is the source of wars, you know. So if you can clearly state, then it's okay.
Yeah, well, I think that will be the last word. I mean, to keep track on time. I think that's also the magic of industrial math. At the end, we move from mathematics to the high sphere of politics and everything. So I think that we can all see that it is a very interesting way of doing mathematics, very like connected to society and the problems of the world. So I shall maybe give the final word back to Amal.
Thank you very much, Christophe, for moderating such a very interesting discussion. Actually, it was very, very interesting. I learned a lot also from all the panelists and from you. And the most important conclusion here is that I think the most important conclusion is that mathematics is about understanding. I think we all have to believe in that. Thank you very much, Christophe. Thank you so much. Now we come actually to the end of this webinar, and I would like now to give the floor to my colleague Ezra Clark, the acting director of the Division of Science Policy and the Basic Science, to deliver the closing remarks of this webinar. Dear Ezra, the floor is yours.
Thank you. Thank you very much, Amal, and thank you, everyone. So really now, after that interesting session, it's just a few words to close, a rather more formal closing. So let me just do that. Thank you. So Excellencies, mathematicians, scientists, engineers, dear colleagues, ladies and gentlemen, thank you to all of you who joined us today in celebrating International Day of Mathematics, and to highlight the fundamental role that mathematics plays in breakthroughs in science and technology, in understanding the major societal and global challenges, in improving quality of life, in empowering women and girls, and contributing to the achievement of the 2030 Agenda for Sustainable Development. And as was very clear today, the focus was on industrial mathematics and how it contributes to sustainable industrial systems, and very interesting too were the interventions and discussions. So let me just express my gratitude firstly to Professor Full for his launch of the French version of the UNESCO toolkit, Mathematics for Action. And of course, to our excellent keynote speakers for their inspiring, engaging presentations, which has provided us with some fascinating insights into how maths helps us solve practical problems in industry and technology. You'll recall Dr. Harrett showed us how numerical analysis and partial differential equations, computer swarms and supercomputers can simulate behaviors, and we had the example related to time manufacturing, but certainly beyond that. Fascinating stuff. And to Professor Fink, who showed us how condition monitoring, operational data, and deep learning can help us detect, diagnose, and predict faulty system conditions. So I hope you found those presentations as inspiring as certainly I did here. So thank you for those presentations. And also, of course, I'd like to extend my appreciation to our moderator, Professor Christoph Ritzenthaler, for leading this lively and engaging discussion between the esteemed panelists. And I think a lot of good and interesting, engaging discussion came out of that. Thank you. So thanks for those thoughtful and thought-provoking contributions and those engaging conversations. Much appreciated. Also, of course, we'd like to thank our partners and supporters. So thank you to the International Mathematical Union for its tireless efforts to promote the importance of maths and support International Mathematics Day. This year, celebration of mathematics for everyone was inspiring, with over 100 registered events globally we know of. We're thrilled to witness the growing interest in maths and its impacts on society. And lastly, really to thank each and every one of you from the participants. I see we had significantly over 150 people, I think, by the looks of it. So thank you all for attending today's event. The active participation, the questions in the chat as well have made this event, I would say, very successful. And whether the audience, you're a student, whether you're a researcher, educator, entrepreneur, policymaker, of course, mathematics offers a wealth of opportunities for creativity, innovation, and discovery. So let's all join forces to promote maths as a global language, or continue to promote maths as a global language of knowledge, culture, and progress, and explore together how maths can help us understand and shape the world and inspire us to pursue new frontiers of knowledge and innovation. So, final word, let's continue to celebrate and promote the beauty and power of maths throughout the year and beyond. Thank you very much to everyone who participated. Thank you very much to the audience. Thank you all, and have a wonderful day. Thank you.
Thank you. Goodbye.
Thank you very much, Ezra. Thank you, Ezra, for
Wonderful.
this. Dear speakers, dear panelists, dear participants, dear colleagues, thank you again for joining us today to celebrate the International Day of Mathematics. Also, I would like, before I end, to thank my colleague Jean for putting this webinar together. I hope I could see you all next year on the same day. And for all of you, have a good day, good evening, wherever you are. Bye-bye. Thank you.
Bye.
Bye.
Thank you.
Thank you.